Hi, dear Mac 202 students. This record is to find some complementary things on riser design and also brief info about the other well-known casting methods. And the last part of this record is to summarize the casting defects, the reasons and the recommended solutions for preventing the defects. Remember previous lesson last week. Lastly, studied on an example. It is just about riser design. Okay, then start from there and then first call the memory and then see some complementary things. Okay, let's start. Okay, you know the function of a riser. Riser mainly is to use as a reservoir. In sand casting, it is to feed liquid metal into the casting cavity during freezing, during solidification. To compensate for solidification shrinkage. Take a pen. To be able to continuously supply molten metal into the cast cavity, yes, here in this example, this is the cavity for having the casting in the end. And what is that? This is the riser. Well, if we can achieve to keep the the metal within the riser still in liquid phase while the material in the mold cavity is turning back to its solid state, then can compensate the solidification shrinkage. You know this. The other function of riser is that, if the porosity of the mold is not so good, while we are pouring the molten metal, the air is to leave the cavity, okay, while the air leaving the cavity, then molten metal fill in the cavity. Air within the cavities can leak and leave the mold thanks to the porosity of the mold. But if the porosity is not in the correct order, then yes, through the riser, then in that case riser is to be open to the atmosphere, to the outside, and through the riser the air can leave the cavities. You know this, but mainly the riser is to feed the molten metal to the cast cavity while the material of the casting is solidifying. To keep the metal in liquid phase within the riser, design the riser such that for which the solidification time is to be greater than the solidification time of the material within the cavity. Numerically, to determine the solidification time, we use Shivorinov's equations, Shivorinov's rule. For riser and the mold cavity, the mold constant is the same because mold constant is a function of the geometry of the mold energy level of the molten metal, and the conductivity of the materials. Well, to be able to have a different solidification time, the variable is not the mole constant. The variable is the volume area ratio. You know, in Shivorinov's equation, well, the total solidification time is equal to a coefficient, mole constant, times volume of the cavity divided by surface area, okay, contact area, power of this ratio, n. That is the Shivorinov's rule, Shivorinov's equation. And in most of the cases, if it is not given, can be taken or can be taken as 2. So it is the square of volume area ratio. Okay, and then, you know, already studied on this example. Well, in the example, the thing to highlight is that, yes, the total solidification time for the riser is 2 minutes, but the solidification time of the for the mold cavity is 1.6 minutes. That is okay. So, well, although the material in the mold cavity turn back to its solid phase, then, well, within the riser can have the metal still in liquid phase, so it can supply the material while the casting material shrinkaging. Okay, but here in this example right now, in the content of today, I want to highlight this design parameter. Well, the riser is a cylindrical riser in shape, and the diameter height ratio is 1. Now that is the question, whether it is the optimum ratio. Well, whether only in this example it is 1, or it is to have 1 in all the cases, because it is the best value. Okay, well, skip the solution, already studied on the solution of this problem, and then, well, bring this question to the interest. Optimum diameter length ratio, okay, for a riser design, or in the geometry of a riser. Well, a riser is a cylindrical riser. It is the most common geometry say to use in riser design. Okay, well, to be able to have the solidification time at the highest order, obvious that the volume surface area ratio is to be maximum. Okay, if it is maximum, then corresponding the solidification time will be in the maximum order. Okay, it's a design problem. To maximize the solidification time, yes, what should be the diameter of the riser? What should be the length of the riser? Well, the volume of the riser is equal to that much, you know, base area times the height is the volume. From here can express the height of the riser as equal to that much. Total contact area, surface area of the riser, base area, tip area, plus lateral surface area. It is equal to that much. Well, to be able to express area, surface area, as a variable of diameter only, substitute L into this expression, and here is the result. Okay, area is equal to that. And then, to be able to make the mold constant, say, to be able to make the solidification time maximum, okay, we know that volume area ratio is to be maximum. Okay, if there is a maximum or minimum value, for instance here, this is the curve of the function, this is the plot of the function, okay, well, in terms of the variable, if the variable is equal to that much, then, well, it is minimum, corresponding value of the function is minimum. Well, mathematically speaking, if there is a minimum value or maximum value, opposite case, then over there the slope of the plot of the function going to be 0. You see, well, the slope is 0. So in this regard, well, if we take the derivative of this function and equate it to 0, can find the corresponding value of the variable. Okay, differentiate this function and then equate it to 0 and solve this equation and find the corresponding value of the variable. It is the diameter of the riser. And substitute the riser into this expression and find the corresponding value of the height of the cylinder. Well, if we do this, we find the expression it is to use for calculating the height of the riser as equal to the diameter value. This means the optimum value of the diameter, optimum value of the height of the riser equal to each other. So the optimum diameter height ratio is 1. Okay, keep in mind a useful info. Design the riser in cylindrical shape. Okay, then what should be the diameter if the height is given, or vice versa? Height is to be taken as equal to the length. Say the diameter. Length is to be taken as equal to the diameter of the riser. Okay then. And then another example already studied, it is to determine the diameter of the riser. The given one, we know the length of the riser, we know the solidification time, it is to be 25% longer for the riser. Okay, then find the diameter of the riser. Okay, already studied on this example. And then, well, already studied on the capabilities and advantages of casting. I don't want to talk about those things one more time. Dear students, by the way, well, I allow you to access to the slides of my presentations, my lecture notes. Well, if I skip a part, then it is not to say that it is to underestimate, not so valuable. Well, I may skip some slides saying that, yeah, well, at home, read the written things, because in preparing the slides of my presentation, I use spoon feeding technique. I wrote all the things related with the things together as the learning outcome. At home, item by item, sentence by sentence, read all the written things on all of my on all of the pages of my lecture notes. Okay, advantages, disadvantages of casting process, already talked about such things. And then, well, there is a complementary thing about cores, especially cores, pattern and core. Pattern, remind you, it is a full-size model of the component. It is the object to manufacture using casting process. Well, the size of the pattern is to be greater than the size of the component, the product. Why? To compensate the effect of shrinkage, and also to have extra material for surface finishing, for machining stage. It is called machining allowance. Okay. Patterns define the external shape of the cast part. If well, at the casting stage, it is advantageous to have the interior features, set the geometry of the interior parts, then need to use well, what, not patterns but also the cores. Well, pattern made of most of the cases wood. Okay, but wood is not a strong material, so well, wooden patterns can be used few times. But if the pattern is made of metal, then it can be used n times. But metal pattern more expensive because can prepare metal patterns precedingly while passing through the casting process. Well, metal patterns are casted. Metal patterns requires well, first wooden models, wooden patterns, and then casting stage, casting process. So can have in the end a metal pattern. Since metal patterns are casted, requires precedingly an additional manufacturing process. Well, these are metal patterns are correspondingly more expensive. But the advantage of metal pattern is that it can be used not only one time, we can use more times. Yes. Okay then, if the cast has interior features and at the casting stage the features, at least some of them, are to create, then it is necessary to use cores. Okay, in this example, yeah, that is the product, okay, to cast, and this is the cavity for having the external shape, and this is the the core. It is to set the interior features, to have the interior feature. In this example, the interior feature is this hole. Okay, so it is a hole, so the core is a cylindrical part. Core, especially in sand mold casting, made of sand particles, and of course, to be able to keep the sand particles in a shape, in the necessary form, geometry shape, we use binding materials, green molding, water, clay mixture with the sand particles. Okay, such a mixture is used. Well, the complementary part in the content of the lesson of this record is on the chaplet usage. What is chaplet? Some cases need to support cores using such special elements. These are called chaplets. In this example, the core is like a cantilever beam. Okay, this is like a fixed support. Okay, this end of the core supported by the mold. Okay, isolate core from the rest of the universe. In statics dynamics, after isolating a part of the universe, this is the core, let's say, I isolated from the rest, then in the jargon we say it is our system and the rest of universe is the surroundings. And then draw the free body diagram. This end of the core has been immersed into the mold, so it is like a fixed connection. The sand particles of the mold applies a force system. That force system can be replaced with a resultant force. Say that F sub m is the resultant of the force system. Okay, it is applied by the malt onto this end of the core. And while turning effect of the force system can be represented by this resultant moment. It is the moment of the forces applied by the malt onto the core. It is at this end. Okay, what else? The weight of the core. Earth attracts all the particles of an object, and the resultant of such an attraction force system is called weight. Okay, if the material of the core has been uniformly distributed, then center of gravity coincides with the centroid of the volume. C is the centroid of the volume, G is the center of gravity. And this representative force is the resultant of the attraction force system. It is applied by the Earth. It is well known. We call this resultant force saying weight of the object. Weight can be calculated multiplying the mass and the gravitational acceleration. Okay, this compact expression comes from Newton's universal gravity law. What else? Well, it is like a submarine. When we pour the molten metal into the cavity, it is going to be a submerged body. If a body is surrounded by a fluid, in atmosphere, the body is surrounded by atmospheric air. So while the surrounding fluid particles apply a certain force system, and the resultant of such a force system is called buoyancy force. And the buoyancy force, that resultant force passes through, line of action of the buoyancy force passes through the centroid of the volume. This is in drawing the free body diagram. Yes, don't forget to show the buoyancy force. Well, if the surrounding fluid is air, atmospheric air, since the density of atmospheric air is in the order of 1.2 kilogram per cubic meter, and buoyancy force from your learning outcome gathered in high school education, and also for mechanical engineering students, there's an introduction course, first year course, Introduction to Mechanical Engineering. In the content of that course already studied, buoyancy force is equal to the density of, not the material of the submerged body, density of the surrounding fluid, Here in casting, the surrounding fluid is molten metal, times gravitational acceleration times the volume of the submerged body. Well, if the surrounding fluid is air, density is 1.2. When we perform the calculation, the buoyancy force relative to the weight of the body and relative to the magnitude of the other acting forces may be negligible. But since the density of, for instance, molten metal is cast iron or steel, density is not 1.2. Density is in the order of 7,800 kilogram per cubic meter is the density of steel, density of cast iron. So it's a big number. When we substitute it into this expression, then can find the buoyancy force as not a negligible force to its effect, to its magnitude. So to its effect, we must consider the effect of buoyancy force. Okay. In core design, totally mold design, yes, it is the question. Well, if the buoyancy force is not equal to the weight of the object, then there will be a net force in the up direction. Buoyancy force minus the weight is called lift force. Lift. It is called lift. Well, shall we balance the lift only having such a reaction force system? It is exerted by the mold. Well, mold is not a strong material. It is made of sand particles. Well, if the lift is too much, then the reaction forces applied by the sand mold to this end of the core won't be sufficient, and the mold will be damaged. Well, the buoyancy lift force will lift the core while it is lifting in the up direction. Well, this part of the mold will be damaged and the core will be lifted, and of course the hole in this example, for instance, won't be coaxial hole with the rest of the body. What can we do? We can use such special supports to balance the lift. Okay, it is called such a support is called chaplet. Okay, well, there is a chaplet here. It is to apply a force. For instance, chaplet is over here, and that is the force applied by the chaplet, F sub chaplet C. Okay, then, draw the free body diagram and be able to find the magnitude of the force it is to apply by the chaplet. Okay. Well, making such a calculation is in the scope under the course title. Be able to perform the analysis and writing the equilibrium equation, be able to find the force exerted by the chaplet or chaplets. Such a studying included to the content of this course. But the rest, okay, after finding the force it is applied by the chaplet, then find the surface pressure. Surface pressure, it is the pressure at this contact surface. Okay, well, the area of the tip of the chaplet is to write as the contact area at the denominator, and the force applied by the chaplet is to write to the numerator, and the force exerted by the chaplet divided by the contact area, this contact area here, it is over there, is the surface pressure here. If the surface pressure exists the limiting value for the core material, we have an allowable surface pressure. If the surface pressure is less than maximum equal to the allowable surface pressure, then that is okay. The core will not be damaged under the action of such a force. But if it is greater, unfortunately, this part of the core will be damaged by the force exerted by the chaplet. Well, this is a design issue. Okay? Check whether surface pressure is less than the allowable surface pressure. If the surface pressure is greater, then yes, increase the size of the chaplet. Use a greater chaplet, have a greater contact area. Yeah, it's a design issue. Well, dealing with this part of the design is out of the content of 202, because making such a control and dealing with the strength of the core material, dealing with the strength of mold material are in the content of strength of materials course. It is in other course in engineering curricula for second year students. But in this course, be able to calculate the force applied by the chaplets. Okay, now how can calculate the buoyancy force and then saying that subtract the weight from the buoyancy force and find lifting force? Well, buoyancy force is equal to density of the surrounding fluid times the gravitation acceleration times the volume of the submerged body. Here is the volume of the part of the core. It is surrounded by the molten metal. Okay. Well, there's an example related with this part of the studying. Casting operation, well, consists of pouring of the molten metal and then solidification stage. At the solidification stage, need to consider the effect of shrinkage, and well, riser is to supply molten metal to the cavity, you know this, and cooling and solidification stage. Oh, okay. Yes, consider the buoyancy, effect of buoyancy of molten metal. Well, to be able to study some problems, related with lift, say, chaplet design, etc., well, can refer such tables to gather the density of material. Well, for some commonly used materials in casting, this manufacturing method, well, can find the densities of the metals: aluminum, aluminum silicon alloy, aluminum copper alloy, brass, cast iron, copper, lead, steel. How about the density of core material? Density of core material, if core is made of sand, can be taken as 1.6 gram per cubic meter. By the way, obvious, in substituting the density, if you need to use SI unit system, then the density is to be in kilogram per cubic meter. If you multiply the given density values in this table by 1,000, then the unit will be kilogram per cubic meter. Okay. And then an example. Well, find the lift. It is the question. Determine the lift. Well, buoyancy force is equal to, in the example, 208 newtons. Weight of the body is 30 newtons, you see. It is necessary to use a chaplet to balance the lift. How much the lift is? Lift is equal to buoyancy force minus the weight of the core. In this example, it is 180 newtons, almost 180. Okay, draw the free body diagram of the core, and then, well, if the lift is equal to that much, then what should be the force to apply by the chaplet? Okay, the rest is to study at home. Okay, the following part of my lecture note is about molds and mold making. Well, to find some complementary things, of course. What are molds and how the mold is made? Well, already studied on such things, but briefly then see some complementary things. Well, I'm not going to read all the sentences one by one, but kindly request you read all the written things on the slides of my presentation at home. Okay? Completely read them, understand and study. Okay. Well, sand mold casting, we use sand particles, silica, okay, mixture with water and clay. Okay. The recommended percentages for the additives in sand mold casting, the volume of sand particles 90%. Okay, 90%, 3% water and 3% clay. If for bonding the sand particles we use water and clay, then in the jargon it is called green mold, green sand mold. Yes, green sand mold. But instead of using water and clay, if we use organic or inorganic chemicals, bonding agents, well, for instance, phenolic resin is an organic bonding agent, well, sodium silicate and phosphate is an inorganic binding material. If we use not clay but such special agents, bonding agents, then the mold is called not green mold but dry mold. Why dry mold? Because, well, this type of molding, well, to be able to increase the bonding effect, the mold is placed into an oven, into a furnace, and it is dried. Okay, it is called dry mold. The properties of sand, well, in sand mold casting are important. One of the characteristic property is refractoriness, the ability of withstanding high temperature. Okay, sand is a refractory material. Okay, itself. Cohesiveness, the ability to retain a given shape when packaged in a mold. Well, cohesiveness is satisfied using special chemicals, but green sand molding, clay. Permeability is important. Well, sand particles are to be in the say correct size order to have the porosity, permeability in the correct order. Well, if the permeability of the mold is not so correct, not in the correct order, then it is going to be only the solution, riser. Risers should be open to the outside, while the molten metal is poured into the cavity, well, to allow the air, trapped air, to leave the region. Okay. And collapsibility is the other characteristic, the ability to permit metal to shrink after it solidifies. Okay. It should allow the metal to shrink. Sand mold is to allow the metal to shrink. Well, thanks to diffusivity, porosity of the mold, well, we can prevent having vacuum within the mold. Okay. Dry sand mold, yes, at the drying stage, it is mold is put into an oven and it is heated at that energy level, 200-300 degrees Celsius. Well, to be able to set the shape of the cavity, well, the sand particles are to wrapped to the pattern. Well, we put the pattern and we pour the sand particles. It is a mixture of water, sand particles, and clay in dry mold, in green mold. In dry mold, some special chemicals, bonding materials mixed with sand particles. To be able to squeeze the sand particles to have the cavity indent in the geometry of the casting, yes, a force is needed. A force is applied to push the sand particles toward the pattern. Okay, if the casting is a small size casting, then that force is applied using a flat plate some tools by the technician, okay, foundry man. But if the size of the mold is greater than a threshold value, then we use a mechanism, a pneumatic system or hydraulic system, to run the piston against the pattern. Okay, using a piston mechanism, we can apply the necessary force to squeeze the sand particles. Or say in industry we use mold preparation machines, mold machines. Well, as it is illustrated in this photograph, on the table we have the flask. Okay, the mechanism of the machine can lift the flask and then drops the flask onto the table. Lift drop. Well, jolty force, jolty displacement, creates impact forces, and those impact forces just to force the sand particles toward the pattern, and then achieve the squeezing stage. And also shake the flask in the horizontal direction, okay, to display the sand particles, okay, in the proper order, to be able to have the sand particles surrounded the surface of the pattern, wrapped to the surface of the pattern. Okay. Jolt type machines just lift and drops the flask, but squeeze type mold machines just slowly, continuously apply the squeezing force using a press. A machine, sand cylinder it is called. Using such a machine we wrap the sand particles at the mold preparation stage uniformly, and have the mold just in the necessary strength order. Okay, in industry we have another casting method. It is called shell molding. In shell molding, instead of having a bulk of sand within a flask, we have a thin shell. Okay, the thickness of the mold is in the order of 10 millimeters. This method in the 1940s developed in Germany, and schematically see the stages of the shell molding. The shell molding, we have a pattern. It is made of metal and it is kept as hot enough. Using electrical resistance, we can keep the pattern at a higher energy level. Or pattern is heated in an oven and then it is placed to the top of a box. It is called dump box. Within the dump box we have sand resin binder mixture. Okay. And then we invert the box, okay, and then the sand particles, sand and resin mixture rains toward the pattern. Since the pattern is hot, then the sand particles together with the binder are cured, okay. They are cured and covers the pattern well, forming a shell. Okay, and then we one more time invert the box, and well, the cured sand particles just will be wrapped and say to the pattern, and the layer will be in the shape of the casting. Okay. Uncured particles dropped, but the cured layer keeps its place. It is a thin layer, it is a shell, and it is in the geometry of the casting. It is in the geometry of the product. And then, well, to be able to complete the curing stage and to be able to make the shell more strong, put the say the pattern together with the shell into an oven, into a furnace, and few minutes heated it up and complete the curing stage. After the curing stage, the shell is stripped from the pattern, and then, well, it is positioned into a box, into a flask, okay, by using metal shots. Well, this part is not made of sand particles, it is made of metal. And we have one half of the mold, it is a shell. While repeating the process, have the other half, and then place the shells into the flask. Thanks to the existence of metal shots, we can position them for having the geometry of the casting. It is the cavity, and then into this cavity pour the molten metal, okay, and then well, after the solidification stage, take it from the box, from the flask. Okay, that is the shell molding. Well, we have not bulk of sand, but we have thin shells made of sand. Okay. Well, the advantage of shell molding, well, the surface quality is better. Average roughness height is in the order of 2.5 micrometer. For an ordinary sand mold casting, it may be in the order of 6-7 micrometer, but in shell molding, it is smaller. It is a better surface quality. And say the manufacturing tolerance in setting the size of the features, the tolerance is smaller, 0.5 millimeters. You know, these are the upper and lower deviations. Lower deviation plus upper deviation is the tolerance. Well, low labor cost, low machining cost, high productivity, shell molding proper for mass production. Okay, but the disadvantage, well, necessary to use expensive metal pattern. Well, we use metal pattern and keep it at a higher temperature. When the sand particles together with the resin are poured onto the pattern, then, well, they are cured because the pattern is a hot pattern. But keeping the pattern as hot, and also, well, requires energy, of course, and also it is to be made of metal. Metal pattern are more expensive, and also, well, within the flask need to have metal shots. Metal shots also expensive components. So, well, disadvantage of shell molding, it is higher cost. Okay. Another casting method is called vacuum molding. In vacuum molding, we do not use binders, but we create a vacuum and we keep the vacuum okay, throughout the casting process. This method in the jargon is called V process and developed in 1970 in Japan. Okay, well, pattern has a special box. Well, this is the pattern, and well, the pattern open to the box thanks to the existence of tiny vent holes. Okay, using a special machine, we suck the air from the box, okay, and keep the pressure within this box as less than the outside pressure. Well, in the technology to use, we have a plastic sheet. Okay, when we create the vacuum saying vacuum, we mean well, the pressure is less than the atmospheric pressure. We do not mean absolute vacuum. Okay, we create a vacuum here. We keep the pressure within this box. It is just under the pattern, less than the atmospheric pressure. So while created pressure difference, this side of the plastic sheet is under the action of atmospheric pressure, while this bottom side is in vacuum. So this plastic sheet is sucked and wrapped to the pattern. Okay, we have the plastic sheet wrapped to the pattern, and it is now in the shape of the casting. Okay, and then well, we have all of such things within a flask. Pour the sand particles, but well, we have no clay, we have no water. These are just sand particles. And then yes, again, thanks to the existence of pressure difference between the atmospheric pressure and the pressure within the box, well, we can suck another plastic sheet. This plastic sheet is to wrap to the surface of the mold. And you see, mold has two plastic films. Well, one plastic film is in the shape of, in the geometry of the casting. The other is flat. You see, we bind the sand particles, in other words, using plastic films at both of the sides. Well, prepare the other half of the mold. Okay, drag and cope, and then place them in alignment, and then have the common cavity. Into the cavity, pour the molten metal. When the molten metal enters into the cavity, the plastic sheets are quickly burns and evaporates. Okay, that is the technology. Since we have no binding material, the sand particles not binded to each other, well, after the solidification stage, we can reuse the sand particles for the next molding stage. So we can recover the sand and reuse. Another casting method is expanded polystyrene casting. Well, the pattern is made of polystyrene, expanded polystyrene. Well, in the literature or in the foundry process industry, we say expanded polystyrene process, or it is said lost form process, or lost pattern process, or evaporative form process. Well, the pattern including sprue, riser, and gating system prepared using expanded polystyrene. See an example. Well, these are the parts of the pattern polystyrene, made of polystyrene, for having the cast in the end. This part is the sprue. That part corresponds to the rest of sprue and some runners. Okay, well, it is this object made of polystyrene, expanded polystyrene. Okay, made of foam, polystyrene foam. To be able to make the pattern say strong to the effect of energetic molten metal, well, we spray a refractory material, okay, to the surface of the pattern, and then place the pattern into a box, and then around the pattern what we have, sand particles, sand packaged around the pattern. Well, this is not a cavity yet, it is just filled by foam, okay, expanded polystyrene. We have here extended polystyrene. And then while we're pouring the molten metal, the polystyrene foam is melt and vaporized, okay, and leave the cavity, leave the region. Polystyrene foam is melt, vaporize, and leave this space and have the necessary cavity for the casting. Yes, well, that's why in this method it is called loss pattern process. Pattern evaporates and leaves the region. Okay, the rest is the same, solidification stage. Okay, well, in expanded polystyrene casting we use polystyrene foams, okay. The other method, it is called investment casting. We use wax, okay. Pattern is made of wax. To be able to increase the resistance of the pattern to the effect of molten metal, we coat the wax with a refractory material. Why this method is called investment casting? Well, investment means not capital, not money to pay, but also the other meaning of investment is covering, okay. Well, the pattern is made of wax and it is covered by a refractory material, so that's why it is called investment, means covering, cover completely, so it is said investment casting. Okay, as an example to understand what is investment casting, see the stages. Well, a pattern is prepared. It is made of wax. Wax is a material, it can be using mold, it can be easily shaped, okay. And then, well, immerse the of course, if the component is not only one but more, then, well, in series and parallel geometry, well, together with the sprue, well, have the others. For having one of the components, for having another component, for having the others, yeah, it looks like three. And these are connected to the sprue. Okay, and then, well, take this pattern and immerse into a bath. In the bath we have refractory material. Refractory material will cover the pattern, and then, well, we supply thermal energy, heat, okay, the tree, and well, wax liquefies, melts, and leaves the region. And after the living stage of wax, we have the cavity. Okay, you see here we have the cavity. Well, we have a shell here. Shell is just made of refractory material, okay. Fully mold is formed by covering the coated tree with sufficient refractory material, okay. During the heating stage, the refractory material will be more strong, but meanwhile the wax melts and leaves the region. And then after that stage, the rest is the same, that of ordinary casting. pour the molten metal. Okay, molten metal will fill in the cavity and diffuse to deeper points, and then after the solidification we can take the castings. Of course, we'll trim the sprue, trim some extended parts, and then we'll split the components and complete the casting stage. That is investment casting. Dear students, at this point let's have a break and then continue on the rest. Have a break.